So we are very pleased to have this opportunity with a very advanced internet system and to disseminate our information to many people in the region. My name is Kaoru Takara, Vice Director and Professor of Disaster Prevention Research Institute, Kyoto University. And I'm the member of the National Commission for UNESCO, as well as National Committee for UNESCO IHP of Japan, as well as Intergovernmental Council of IHP. I'm Vice Chairperson. So I'm very happy to have you all in this lecture in this classroom in Kyoto University and many classrooms in maybe Japan, Indonesia, Bangladesh, Malaysia, and the Philippines. So today's lecture will be supposed to up to 2 hours and a half, but 1 hour later I will take 15 minutes break. And now Japan standard time is 2 o'clock in the afternoon, and in Indonesia almost noon. And I don't know, some other countries maybe 1 hour, 2 hour, 3 hour difference. Anyway, 1 hour later I will take 15 minutes break. Okay. So now I'd like to start my lecture. Today's lecture includes introduction part, including countermeasures against extreme events and climate change, and basic theory of frequency analysis of hydrological extreme events. Further issues not described in the textbook. Textbook has only 12 pages, so I mainly describe the basic hydrological statistical analysis schemes or method or theory. But some further issues are presented now, today, in the second half of my lecture. And also trend analysis and use of GCM output. GCM stands for Global Climate Model or General Circulation Model. So first, introduction part. This view graph shows flood management before modernization. It means before 1950s. We had various kinds of traditional flood control measures, and it had been successful, but not so much modernized. But this kind of indigenous technologies and adaptive lifestyles were developed earlier and still effective even today. So this is, you may see some of the flood control measures in Japan traditionally and also in modern times. And Japanese government constructed of flood diversion channels as shown here, and construction of flood retarding basins. This is also very useful flood control measures. As well as those, we constructed many dams and levees and so on. And this graph shows the time horizon, and the y-axis shows the number of persons killed. Since 1945, before many people were killed, about thousands of people were killed per event by typhoons and floods and so on. But our river improvement measures have been successful to reduce the number of victims in terms of floods, disasters. And this is a very interesting urban flood situation in Tokyo, the Kanda River. Kanda River is very urbanized river, very small one. And in typhoon event, the Kanda River will be something like the right-hand side photo. It is almost flooded and many economical damages will be coming during such kind of flood events, even in today. And this is the multi-purpose flood retarding ponds and underground storage which are installed in Tsurumi River Basin, south of Tokyo area. And we have various kinds of flood control facilities like this. And stormwater detention ponds and infiltration facilities in urban areas, regulating reservoirs, stormwater retarding facilities, and permeable pavement, infiltration pits, etc. So in rainy season or flooding situation, those facilities are effective for reducing flood peaks and so on. And this shows the super dikes, so-called, at Osaka City in the Yodo River Basin near Kyoto City. And the left-hand side photo shows some space where factories were at the riverside. But the space is now occupied by the residential area like this, like a right-hand side photo. So this kind of super dikes are built in Osaka, Tokyo area, basically. And those river planning and flood control design done by some technology. We design rainfall or design floods. Sometimes we say 10-year return period, 5-year return period, 100-year return period, and 200 return period, and so on. So this kind of concept is derived from frequency analysis. And we use probabilistic or stochastic approaches. Basically, this analysis and approaches are based on stationary assumption. Our hydrological system is stationary from year to year, but recently climate change may affecting this stationary assumptions. So somebody said it's already non-stationary situation. So a traditional frequency analysis method doesn't work in the future. Somebody said that. I will discuss this matter later. This shows the recent change in climate. The upper graph shows the daily rainfall over 200 millimeter is significantly increasing in Japan. So before it was 3.5 days average over 1901 to 1930, but the incidence of daily rainfall over 200 millimeter become 1.5 times